So let's say alpha is algebraic of degree n over a field. The smallest field containing f and alpha, as we've seen in the last video, is the field that looks like elements of the following form. You could take powers of alpha and form their linear combination with elements in the field f. What I'd like to prove to begin this video is that such a linear combination must be unique. So the new content of this theorem that we hadn't seen in the previous video is the uniqueness property. So here, let me prove this. So suppose that I could write beta as a linear combination of these powers of alpha, so a0 plus a1 alpha, all the way up until I get to a n minus 1 alpha to the n minus 1. Let's suppose I could write this beta as a linear combination in two different ways. So I could also write it as b0, this is also beta, plus b1 alpha up until I get to bn minus 1 alpha to the n minus 1. So if I have two different expressions for beta, I could subtract them and find that 0 is equal to a0 minus b0 plus a1 minus b1 alpha all the way up to an minus 1 minus bn minus 1 alpha n minus 1. Now, I'm hoping that these coefficients a0 and b0 are the same, a1 and b1 are the same, and so on. I'm hoping that all these terms are 0. That's indeed the case, because then I could take a polynomial p of x to be a0 minus b0 plus a1 minus b1 x plus an minus 1 minus bn minus 1 x to the n minus 1. This is a polynomial with coefficients in my field. This has alpha as a root. Now, this is a degree n minus 1 or smaller polynomial. And the degree of alpha is n. That means the smallest degree polynomial that has alpha as a root is n. Here's a polynomial that has smaller degree with alpha as a root. Thus, the only possibility is that this is the 0 polynomial, meaning that all the coefficients are 0. So that means that ai equals bi for all I. So that proves the theorem. That proves the uniqueness property, because I wrote beta as two possibly different expressions, but then showed they were actually the same expression. So what does this theorem actually say? This theorem says that f adjoined alpha, which is the same as polynomials in alpha with coefficients in f, if alpha is algebraic of degree n, I'm still saying that alpha is algebraic of degree n, this is an n-dimensional vector space. Over f. So I know that if you're in this class, if you're seeing these videos, then you've been exposed to concepts from linear algebra, at least in a very beginning course, where you've seen the idea of vector spaces. Now, a vector space, recall, is just a set together with a set of vectors with an ability to add two vectors and multiply by scalars. That's what I'm doing. A vector space has a basis. The dimension of the vector space is the number of vectors in the basis. And every element in your vector space is a unique linear combination of your basis vectors. So this here, these powers of alpha, that's my basis for a vector space. So this could be a little bit mind-blowing at first because this is a field and a vector space, both at the same time. It has a basis. We could talk about linear independence and linear dependence. We could talk about dimension. Let's do a couple of examples. So let's look at R adjoined the complex number I. This is just every number of the form a plus bi, where a and b are real. We're comfortable saying that these are the complex numbers. So the complex numbers are a vector space. It's actually a two-dimensional vector space. So this is a two-dimensional vector space. Over R. Now this is a fancy way of saying that complex numbers are linear combinations of 1 and I. A basis is 1 and I. So every complex number is a unique linear combination of 1 and I. Let's do one more example. How about we let omega be a fifth root of unity? So e to the 2 pi I over 5. So that's a fifth root of unity. What that means is omega to the fifth power is equal to 1. It's a complex number. So then omega is a root of the polynomial x to the fifth minus 1. And that's a polynomial with coefficients in the rationals, let's say. So then let's find the minimal polynomial for omega. So the minimal polynomial it's not x to the fifth minus 1. That's certainly not the minimal polynomial because 1 is a root. If I plug in x equals 1, I get out a 0. So it has a root and it could be factored into two smaller polynomials. In fact, we could see, well, let's find the minimal polynomial. It's not what I'm going to write down right away. We could see that x to the fifth minus 1 can be factored. 1 is a root, so it has x minus 1 as a factor. And then you can do a little bit of algebra and see that this will be x to the fourth plus x to the third plus x squared plus x plus 1. Now this polynomial has no roots that are rational. The rational root theorem tells us that such a root would have to be plus or minus 1, and neither one actually is a root. So no rational roots, and then you can prove explicitly, or I believe we've actually done exercises similar to this in the homework, that this specific type of polynomial is irreducible. So this is irreducible. It has omega as a root. This is my minimal polynomial. It's a degree 4 polynomial. So therefore, what I'm showing you is, thus, Q adjoined omega is a four-dimensional vector space over the rationals. What is a basis? 1 omega, omega squared, and omega to the third. So every element in this vector space is a linear combination of your basis. It's a unique linear combination. So it's not only a field, it's also a vector space. Okay, great.